Okay, so at this point in optoelectronic semiconductor devices, we are ready to talk about lasers. And I will also touch on briefly today some silicon photonic devices as well, meaning silicon devices used to modulate information in an optical manner. So, to begin with, you've got some different laser diodes that are shown here. Some of these are diodes, some of these are other type of lasers. And the key innovation that has really exploded a lot of applications of lasers was the development of blue LEDs and the blue lasers, both by Suji Nakamura, who was at Nichia Chemical at the time when he did his work in Japan. And so again, the same technology used that created blue LEDs, he was able to also demonstrate some of the first laser diodes as well, based on gallium nitride technology. I mean the first blue laser diodes, that is. A little bit more on this general area. So this lecture is going to start to touch on topics in optics, which is beyond the main scope of this course. If you're interested in anything more in learning on this topic, I offer a course next year that's for seniors called Optics for Engineers. It's a combination lab and lecture course. And so if you think that you'd like to learn more about optics and electro-optics, then I encourage you to consider taking this course as well. So, back to lasers. So the word laser is an acronym for light amplification by stimulated emission of radiation. And the laser is a special source of light that has three unique properties. The light is always highly directional, it's monochromatic, meaning it's almost a single wavelength, and all the photons are in phase in terms of their peaks and valleys for the electric fields and magnetic fields. Now, since lasers were first developed, they've become commonplace for all sorts of devices, those including those in conveying information. Some of the applications include telecom, optical storage, laser pointers, speed rangefinders, construction, printers, etc. You know, the list could go on, but the main point is that a laser is a great example of why we have basic research. When the laser was first discovered, they were searching for these applications. They had not even thought of a lot of these. And so it's a good example where you do have to do basic discovery and research, and then the application sometimes will follow. A little bit more in the history. The first concept of a laser that was detailed and adequate in the level of detail we'll see today was by a graduate student, Gordon Gould, at Columbia University. And it's pretty interesting. You'll notice some things here, and if you read through this after we do the lecture, you'll notice he's talking about a lot of the same design principles we talk about today. So he had a great vision of how you can make a device like this, and you'll see that it's the exact same principles we covered today. The first visible light laser was a ruby laser. It was basically sapphire, aluminum oxide, doped with chromium, and that was by Theodore Maiman. Basically, here's the sapphire rod, and then they flash it and pump it optically using photoluminescence, but we'll talk more about that later. The first laser diode, meaning electrically pumped laser, was by Nick Holniak Jr. In 1962. He's actually a faculty member at University of Illinois right now as well. And there's the first laser diode emission you could see from his device there. Okay, so let's figure out how a laser works, and let's start with light absorption and emission. Okay, so let's start with a semiconductor at room temperature. And you'll see the way I'm drawing this is important. I've got some electrons here, and anytime I thermally generate an electron, right, it creates a hole, okay? And so I've drawn that with positive charge down here. Now note, these circles are representing silicon atoms. And so anytime a silicon atom gives up an electron, that's a hole, right? And so the rest of these circles are just silicon atoms where there are electrons down in the valence band, hence no holes for those. That'll be important a little bit later. Okay? Now we know that for a semiconductor that we could have photons of light come in that could excite generation of a electron hole pair, and then one of these circles will get a positive charge, meaning that silicon atom is missing an electron, which is a hole. Okay? We can also have non-radiative recombination, meaning it basically generates phonons or vibrations, where the electron goes back down here, and that'll make this just a circle without a positive sign in it, just a regular old silicon atom. And as we've learned previously, if we have a light-emitting diode, we can get spontaneous emission. That's an important term, which is going to start to differentiate when we talk about LED lasers, that is. Spontaneous emission means that I have electrons and holes. They can at some point randomly or spontaneously line up, recombine, and a photon can be emitted in any direction at any time. And so it's spontaneous. It's not something that you necessarily control or predict. Electron-hole pairs line up, photons emitted. It can go in any random direction. Spontaneous emission, the basis for LEDs. Now, let's go on to the special type of emission which is necessary for a laser, which is stimulated emission. And in stimulated emission, what happens is I've got electron-hole pairs that are they're lined up, they're ready to recombine, okay? But they're not ready to recombine yet based on spontaneous emission. That would take a little bit longer time. But what happens is a photon comes in, this blue photon here, let's say, or let's say the black photon comes in. The black photon comes in here, and it basically stimulates the recombination and generates a second photon, which is in the same direction and same phase, meaning the peaks and the valleys line up, as the photon which stimulated the emission. In terms of quantum mechanics, how this sort of works, and if you want to learn more, you have to go over to physics, and you could take a year-long course that'll teach you how this works on quantum electrodynamics. But for now, basically what happens is the electron-hole pair is sitting there, and it would like to recombine, but it takes some time, right? We have a recombination lifetime before that occurs, so it doesn't happen instantaneously. And what happens is the photon comes along and basically gives it a quantum mechanical blueprint of how to give up its energy. The electron-hole pair wants to give up its energy. Photon comes along and says, here's a perfect blueprint of how you can do that right now immediately. It gives the electron-hole pair that blueprint, and then that second photon is created using the blueprint of the first photon. Okay? Now, achieving stimulated emission, which is what drives things inside a laser, is easier said than done. One reason it's difficult to get the photon to the electron-hole pairs because most of the time the photon will be absorbed first. So think about it. If this photon has if I have an electron-hole pair recombination which can create the second photon, that means the second photon will have an energy greater than the band gap, right? And that means this first photon will have trouble getting to this point because it could also be absorbed by the semiconductor because it obviously has an energy greater than the band gap as well. So it's difficult to get to those electron-hole pairs before the photon is absorbed. The other thing that's difficult is that if you want this to work in stimulated emission, I have to have a photon get right next to this electron-hole pair before it undergoes spontaneous emission, before it recombines by itself and spontaneously emits, which would be this emission in any direction, right? Any time, any direction. And so it's difficult to have enough photons in there at all times to be able to catch and stimulate recombination as opposed to having spontaneous emission, which would be in any random direction. So both of these make it difficult to achieve lasing. So there are a few additional device aspects that we need to add, else we'll just have a regular LED, we won't have a laser. So let's start to take a look at those. So the first thing we need if we want to have a laser, different than an LED, is we must have population inversion. Population inversion means that I have more electron-hole pairs generated or created than I have electrons in the valence band. What I'm saying by saying this is that there are more electron-hole pairs ready to recombine than there are electrons down here. Look how I've drawn this. I now have more positives here and electrons corresponding with them than I do have the circles with no positive charge, which are electrons down with the silicon atoms. What's this mean? Well, basically this means that a photon is more likely to encounter an electron-hole pair than it is to encounter an electron in the valence band, which would cause the photon to be absorbed. This is what I want for lasing, basically. I would like photons to come in and basically see electron-hole pairs, which can give me stimulated emission, and not see things like electrons down in the valence band, which instead could be absorption, because the photon could kick the electron up here. In fact, if you think about this, if I had nothing but pure electron-hole pairs here, and there were no electrons down in the valence band, then there would be no way to have optical absorption, right? So you actually see your optical absorption could go down as a result. So for this type of thing, you ask yourself, what's just better, carrier lifetime that's long or short? You want long carrier lifetimes, meaning you can start to basically try to invert the population, where I have more electron hole pairs than electrons in the valence band, and then they'll stay there long enough to maintain that population and then get stimulated emission. Again, it's called population inversion because normally with a semiconductor, you'll have more electrons down here than you will have holes. And you'll normally have more electrons in the valence band than you will have electron hole pairs. So you're inverting that to the point where a photon will start to see more electron hole pairs than electrons in the valence band. So how do you do this? Well, how can we electrically inject such a large excess of electron hole pairs? Well, we could have N-type material on one side of this thing, one side that has tons of electrons. We could have P-type material on the other side that has tons of holes, and we could basically have a PN junction which injects the electrons from one side, the holes from the other, and then gives you population inversion. So again, a diode is coming back to play in this course. So, let's use a PN junction to inject electron and hole pairs on both sides. We get population inversion, so assume I've got, N-type over here, P-type on the, whoops, I didn't mean that to happen, P-type over on this side, and we get our population inversion. The challenge, though, is if you build up a high concentration of electron and holes, you know that they want to spread out, right, because of diffusion. So we've got to have some way to confine those. So the next thing you do, in addition to having a PN junction, is you use a double heterojunction again, like we did for LEDs, where I've got wide band gap on both sides of the active region and narrow band gap here in the active region. What that does is I can pour in electrons, pour in holes, and they will stay trapped in here and not diffuse out because of diffusion, because you build up a high concentration here. Again, if I want population inversion, I've got an enormous concentration of electrons and holes. And so I want to trap them here so they don't just spread out when I try to, after I've injected them in, and I use a double heterojunction to achieve that. Well, here's my conduction band, here's my valence band. So if you do all this, you have made a useful device, but you haven't made a laser yet. What you've done at this point is you've made a semiconductor optical amplifier, where you've got population inversion here in the active region by injecting electrons from the N-type, holes from the P-type, and if I bring in a photon here, it could amplify, stimulate, emit, and result in multiple photons coming in the other side, hence semiconductor optical amplifier. What's this useful for? We'll talk a little bit about on the next slide about that. And again, note, this is not yet a laser. We have to add one more device design aspect, and I'll get to that in a moment. So what can we use a semiconductor optical amplifier for? Well, one of the uses it's commonly used for is short haul optical fiber networks where you need to do some amplification. And so let's say I have in your neighborhood, they bring in the signal that comes from the main line, fiber optic line, and then it's got to go to all your houses, right? And it's too weak to basically be detected by all the fiber optic receivers in your houses if you got one of the new faster internet fiber to the home. Well, what you'll do is you'll have all these semiconductor amplifiers, which will bring in a few photons can come in, and which give you a significant amplification of photons out the other side. So basically, if I have a data pulse that's coming in, and it looks kind of weak like this, and here's my ones and zeros, it goes through the semiconductor amplifier, and as it comes out the other side, I will see much stronger amplification of the signal as a result of the semiconductor amplifier. How much amplification can you get? Well, this device over here, you have to put a ton of current through it because getting population inversion is not easy, right? So this thing requires 450 milliamps. But when you do that, you can see here your optical signal can be amplified 5 to 30 dB, which is 3 to 1,000 times. So you get a significant amount of amplification with this thing. And so also I'll note for this thing that this is meant to operate in infrared wavelengths. There's two types, one around 1300 nanometers and one around 1500 nanometers, which are the typical telecom wavelengths. We'll talk more about why we choose those wavelengths in a little bit. So, why don't we get lasing? Well, again, the problem with the above approach here is that we only get photon amplification if we provide some photons at the input. If you do nothing with this device, there's no significant photon output out this side. So you have to feed in a signal this side to basically get a significant signal out the other. So if I take away the input signal, this device really doesn't do anything. So what are we going to add? Well, we'll get to that in a moment, but let's first do some review and take a break, and then we'll talk about the next step you need to make a laser. So a couple questions here. Spontaneous emission, like that an LED occurs in, pick one of these options. Stimulated emission requires, answer here. Stimulated emission produces, pick one of these answers, and two true-false questions. Then we'll go on and we'll finish off and tell you how you make a laser.